Hello, and welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be starting a new module, Hypersonics, and we'll look at the particular ideas of hypersonics. What is hypersonics? Where did the name come from? What makes a flow hypersonic? We'll understand this through a particular definition and, of course, some examples. We'll then look at the idea of Mach number independence and make some final observations. So this is really a physics-based type class, but really not without too much mathematics. So we just want to get a general physical understanding of what hypersonics is. Let's look at some of this now. Let's start with a quote by none other than Dr. John von Neumann, who we've already talked about in this class. He was quoted in Life magazine in 1957 during the Cold War. He said, "If you say, why not bomb them tomorrow? I say, why not today? If you say today at 5 o'clock, I say, why not 1 o'clock? And of course, he was talking about nuclear weapons and their use, of course, in the Cold War to remove the enemy in a first strike doctrine. This was the kind of person he was, which is an interesting quote because he's frankly one of the top 10 smartest people who lived in America in the last 150 years. Why would he say something like this? And you have to understand and take the context of the quote at the time. To help understand this philosophy, we'll look at hypersonics. Here's some particular notation that we'll be using in this class. Hypersonics community often uses a little bit different notation in its original development. And we'll try and stick to this notation as closely as possible. These particular hypersonic classes I'm showing are based on, of course, the work of Shapiro, and will follow his philosophy and development of hypersonics. But of course, Shapiro didn't invent these types of things himself. They were actually invented by a large group of people over many decades, and we'll be noting a few in particular as we develop the course. Take a few seconds and study these nomenclature so they're familiar to you through the lesson, and I'll try and relate the nomenclature to our past nomenclature as we move along. Let's look at particular hypersonic examples. Here's one of my favorite pictures ever from NASA. Here is none other than Neil Armstrong, the first American on the moon, and first man on the moon actually ever, first person, standing by the North American X-15, which is of course my favorite aircraft. This is after it's landed. It's a hypersonic aircraft. Notice where he's standing. This is the leading edge of the aircraft, and it's actually a sphere. It then has a very low angle as the flow moves downstream over the nose of the aircraft. This shape is chosen for a lot of reasons, which we'll explore in this particular class. It's also chosen for the effect of aerodynamic heating, which we'll talk about in another class in hypersonics. Here's a more contemporary vehicle, and I'll read the figure which I've written. This is the NASA HyperX program X-43. A wing booster rocket with the X-43 was placed on top called a stack. It was dropped and launched from a B-52 Stratofortress in flight. After the booster rocket, which is basically a rocket that brought the hypersonic vehicle up to speed and then separated from it, brought the so-called stack to the target speed and altitude. It was then discarded and fell to the ground. The X-43, pictured here, flew free using its own engines, which is a scramjet, and we already talked about this type of technology in previous classes. The first plane in the series, the X-43A, was a single-use vehicle, so 3 of them were built, and the first one was destroyed after malfunctioning in flight. The other 2 flew successfully, with the scramjet operating for approximately 10 seconds, followed by a 10-minute glide and intentional crash. Here the vehicle's flying from left to right, as pictured in this artistic rendition, and the airflow goes under the vehicle and is compressed by the shock and goes through the engine. It reacts through combustion, injected fuel, and expands out the trailing edge of the vehicle. This is indeed designed to fly at hypersonic speeds. Let's look at another of these types of vehicles called the Waverider. This is the picture of the X-51A Waverider, courtesy of the United States Air Force. It's an artistic rendition once again. Of course, this vehicle has also performed flights for hypersonic research testing. Here's the leading edge of the vehicle, moving at hypersonic speeds. And once again, there's a compression shockwave which moves down and a multiple ramp, which we looked at in our oblique shockwave module, and goes into the face of the engine, where it's then, of course, compressed and then goes through combustion and expands through a nozzle out into the atmosphere to create thrust. Look at the particular shapes of this vehicle. In fact, the shape of the vehicle is designed to create a wave, a shock wave, which creates the lift. So Waveriders are types of vehicles where instead of, say, using a traditional wings to create lift, that they create a shock wave system and they ride the waves through the atmosphere, which creates the lift. This is a very different concept than, of course, using traditional wings. These are called Waveriders. You can imagine that they ride the wave through the atmosphere, which, of course, creates the lift through the shock system about the vehicle. Here's the X-51A in practice, which is not an artistic rendition, and mounted on a B-52 in 2009. So this is the same rendition. Here's the leading edge. Here's the engine inlet, and there's the nozzle exhaust, and here's a rocket engine which separates from the vehicle, as shown here. Can flip back and forth. So this is during the boost phase of the vehicle. Let's look at another example. We can also see a very similar engine being tested at NASA Langley. Way back in the beginning of the class, I showed the exhaust duct from this particular hypersonic wind tunnel. Indeed, my students and myself, when I was at NASA, walked right down this test section, of course, when the tunnel's off. Here in this case, we're looking downstream in the tunnel in the open test section. This is the bottom side of an engine where there's an inlet, the duct with combustion chamber, and of course the exhaust, which creates thrust. So this is a full-scale vehicle test at Mach 5. In this case, they consider Mach 5 to be the hypersonic test condition. This is another example of a hypersonic vehicle, which is a Waverider. Here's another version. This is from the People's Republic of China. This is the so-called Chinese Project 0901 flying vehicle, which is a slightly different configuration. This is in the boost phase before it enters air-breathing hypersonic flight. So the rocket will boost the vehicle to the cruise Mach number at hypersonic speeds, and this part will separate, and then of course this part of the vehicle will become the air-breathing hypersonic vehicle. In all these cases, they have very similar shapes because they're riding the waves and they're creating a compression ramp which goes into the air-breathing engine and exhausts through the exit. These hypersonic test facilities I've had the luxury of visiting, and we already talked about how supersonic wind tunnels operate. Hypersonic wind tunnels operate basically through the same principles. In fact, they have a bottle field and often a vacuum sphere and a test section, and the wind tunnel blows down. Here at NASA Langley Research Center, that's me pictured right there, I'm standing behind, or in front of that is, the bottle field for one of the hypersonic test sections. Now, if I look to the left, we can actually see the building where the hypersonic engine test sections are located in a second. This is one of the vacuum spheres, so this high pressure bottle field here, thousands of long cylindrical tubes have pressure raised in them, which hold the high pressure air, which exhausts down through these large spheres, which of course are vacuum spheres. So before the test, all the air inside these spheres is removed. And then the test can begin by opening some valves, essentially. And of course, these tests can run on the order of minutes, usually, if it's a large facility. Here's the actual test section facility itself. You can see another vacuum sphere here at NASA Langley, the large white ball. And you can see the scale of this particular building. This is where there's basically hypersonic engine test cell A and B on the left and right, respectively, through these large concrete doors. So the first floor holds the engine test sections where we do fundamental experiments in hypersonic flows. And the second floor and above holds all the instrumentation rooms. So the walls of this building are very large concrete reinforced steel structure. But the roof is basically non-concrete. It's not reinforced at all. In fact, there's just a basic metal roof. Why is this? Well, of course, if there's a problem in one of the hypersonic engine test cells, there'll be an explosion. And the building is designed so that the explosion goes up into the atmosphere and not out sideways where people might get hurt. Of course, the test engineers are above the engine facility because, of course, the walls are multiple feet thick of concrete. And so the test cables and computers running the test are all located above the test cell. It's an interesting configuration, but it's done for the safety of the public, not necessarily the test engineers. I've had the luxury of walking through these buildings of the historic hypersonic engine test cells, which were likely some of the first fundamental hypersonic air-breathing engine test cells in the world. And if you get a chance to walk through this building when visiting NASA, I highly recommend trying to take the tour. Hypersonics is not only for, say, air-breathing engines or vehicles returning from the atmosphere or entering orbit, it's also occurring in natural phenomena. Here's an example from a meteor reentry in Russia, which created a fireball from a meteor that exploded in Russia, of course, on February 15, 2013. Indeed, it was such a high-speed vehicle that it created a shockwave that shattered windows and injured more than 1,000 people. The Mach number was at a hypervelocity flow, probably between 20 and 30. Anyway, the buildings under here all had their windows shattered, and unfortunately, people have suffered injuries. This cloud here is where, of course, the meteor went from left to right, and it was actually captured on different people's car dash cams. You can look this up on YouTube if you're so curious about seeing it. Now let's look at some particular schlieren of the hypersonic devices. Here's a projectile moving from right to left in a particular wind tunnel with a high-speed camera capturing it as it passes the frame. This medium here, which is a Schlieren image, is undisturbed, and recall that Schlieren images show density gradients at light or dark colors away from the ambient medium. Here's the vehicle itself, which of course light can't pass through, so it appears as a black or dark object on the exposure. And then we see these particular lines, which are, of course, oblique shock waves attached to the front of the vehicle. Now, one thing about hypersonics that we can characterize physically is we see that the angle, the turning angle of the flow, which is defined by the turning angle of the flow of the vehicle, that is its angle with respect to the incoming flow direction, is almost equal to the hypersonic shock waves which form. So the shock wave angle beta and the turning angle of the flow theta are almost equal in hypersonic flows. And this is, of course, because they're stronger shock waves. Of course, shock waves, which are higher and higher speed, also have stronger losses. Remember, this is a nonlinear phenomenon. But remember, in hypersonic flows, we characterize them by having shock wave angles which are close to the vehicle's surface, like you see in this picture. Here's another picture of a very similar flow. This is a particular shadowgraph image of a ballistics facility shooting a projectile from right to left, and the speed of the projectile is about Mach 6.7. This picture was taken so that the projectile is on the left side of the exposure, and the shock waves wrap around and turn back behind the vehicle. You can also see there's two trailing shocks which are containing the hypersonic turbulent wake, which isn't seen very closely in a shadowgraph image. Here, of course, the 60-degree angle is the total angle of 30, half angles of 30 over the cone. So this is considered a hypersonic flow, because of course it's at high Mach number. Generally, we look at hypersonic flows as Mach number 5 and higher, but of course, that's not a very rigorous definition. And in this series of classes, we'll try and derive a more rigorous definition for you. Here's another beautiful image. This is a Schlieren photograph of a sphere moving right to left through an image. Here we see both the trailing and leading oblique shock waves, which are at very small angles relative to the flow direction, and the Mach number here of the sphere through the facility is 12.1, which is a very high Mach number, but it's still hypersonic flow and not hypervelocity. Inside the flow, you can see a beautiful turbulent wake, which looks like these granulations of the flow. And so the turbulence behind these bodies is often considered to be highly compressible turbulence. And there is indeed a difference between incompressible turbulence and compressible turbulence, which is a little bit beyond the scope of this particular class. Now, I usually show in class this video from the NASA in 2009 where they published a 1950s video of Langley Center's 11-inch hypersonic tunnel. They put in a number of models and watched them disintegrate because of the aerodynamic heating. So hypersonic flows often become so hot and heat up the devices in the flow so much that they can melt steel or even exotic aerospace materials. We'll try and watch this video in our one-on-one class discussions. Let's take a minute and just look at a particular test facility from NASA. This is actually a handout which they give to, say, customers or companies who might want to come in and use their 8-foot high temperature tunnel. There's multiple hypersonic tunnels throughout the world, and this is just one example. I'll let you read through this on your own. Now that we look some test facilities, some natural occurring, say, media coming through the atmosphere and disintegrating at hypersonic speeds, and some air-breathing applications, let's now draw this physical phenomena so we can better understand it. In hypersonic flows, we might say that there's a temperature entropy layer, which is very unique relative to the boundary layer flows at lower speeds. In the top figure, we might show a thin shock layer at hypersonic speeds. And as we noted earlier, in particular examples, the shock wave is very, very close to the vehicle. We might call that a thin shock layer at, say, Mach 36. So we see the shock waves always being very close to the vehicle, which is one physical phenomenon we see in hypersonics. In the little figure, we might see the interest and zoomed in view of the boundary layer, which might have a different thickness than the so-called entropy layer. That is a large layer of high temperature flow, which is hotter than the ambient environment. And of course, we'll see that the temperature at the vehicle's surface is actually lower than the temperature in the neighboring fluid in the entropy layer, or that is, it's just a high temperature layer at hypersonic speeds. Here's one drawing of this type of layer. If we zoom into the wall between, say, the edge of the boundary layer of temperature and where the shock wave is way out on top, we might draw the temperature profile. For example, the temperature of the atmosphere we might draw at the boundary layer edge and draw a dashed line, and that's what we might call TE. But the actual temperature profile, which is a function as the distance from the wall at any one point of the vehicle, we might write as TW. So the actual temperature at the wall of the vehicle is TW, which can often be 1,000 or 2,000 Kelvin higher than the ambient flow field, easily. And if we step away from the wall in the Y direction, we'll actually see that the temperature increases to the maximum temperature and then decays back down through this temperature or entropy boundary layer to the ambient value, which is T sub E, the edge temperature, which is of course higher due to the shock wave than the actual ambient. So you see the maximum temperature in the flow is actually off the wall, which is very counterintuitive relative to our early developments in low-speed supersonic flows. This is why temperature considerations are so important. And in fact, they're so important that it changes the dynamics of the fluid in the boundary layer of a hypersonic vehicle. Let's look at another figure. Here we see a small cone with some viscous interaction effects. This means that the viscous effects are most important near the leading edge of the cone and less so downstream. In fact, we often have a laminar flow coming in at hypersonic speeds, which transitions to turbulence and then becomes fully turbulent in the boundary layer. Here's a graph of pressure over the ambient pressure with respect to position in inches on this particular half degree of 5 degree cone at Mach 11 and Reynolds number 188,000. We might also look at a particular bow shock. In this particular case, at say Mach 36, we might have an outline of a capsule which holds astronauts returning from space. A bow shock forms in front of the vehicle, as we've shown previously. Let's zoom into the area between the bow shock and the leading edge of the vehicle, where of course there's heat transfer from radiation and convection going into the vehicle, which has to be dissipated. At Mach 36, through the bow shock, we'll have a rough static temperature of the fluid of about 11,000 Kelvin. We cannot calculate this with our perfectly perfect gas theory, which we previously developed for normal shocks. You'll get a different answer because of the assumption. We can no longer make the assumption of calculate perfect gas in hypersonics, which you'll see momentarily in this class. Indeed, at this temperature, the fluid becomes partially ionized, and the fluid, which is a gas before the shock, goes through the shock, and the temperature is raised so much that the fluid, which is an air in this case, or atmosphere of another planet, becomes a plasma. And so we have a plasma. The fluid becomes a plasma behind the shock. And of course, this creates a large amount of radiation heat transfer into the vehicle. And not only that, of course, it's a hot fluid, so it also heats up the vehicle through the convective heat transfer. So we now have to understand ionized gases and plasmas and dissociated gases and all kinds of atmospheric chemistry problems when we're dealing with hypersonic flows if we want to predict the right flow fields and temperatures. This is obviously an added challenge to the whole field. Let's look at how drag changes with particular Mach number in the flows. Here we have the drag coefficient for a particular sphere and a cone cylinder from a ballistic range measurements. And we've plotted the measurements as pluses and x's respectively for the sphere and cone cylinder. And on the x-axis, we have an ambient Mach number. That's the Mach number at which the vehicle flies, the sphere or the cone cylinder. The Mach number goes from 0, 2, 4, 6, 8, and 10. The y-axis is the coefficient of drag, defined, of course, as the diameter of the so-called cone cylinders. Let's look at the particular sphere first. At Mach 0, or very low speed, we have a small coefficient of drag. As we approach the transonic condition, we get drag divergence, as we discussed in the transonic module, and it rises like a barrier up through about 1.5. Then we hit Mach 2, and we're still in the supersonic regime, and we come down to around, say, Mach 5 for the sphere, and it levels out. And so drag has become independent of Mach number at about Mach 5 and larger. For the cone cylinder, our drag once again rises like a barrier, and we come up to about Mach 1.75, and then it quickly reduces after the transonic and supersonic ranges through the hypersonic ranges, which start around Mach 5, and then levels out. So you can see in both cases, Mach number is independent of drag. This is the so-called Mach number independence of hypersonic flow. Now, Mach number is no longer a good similarity parameter to, of course, compare wind tunnel experiments with flight tests or to collapse data, because, of course, Mach number has no bearing on the particular coefficient of drag, which is bad because, of course, we can no longer do, like in subsonic flows, our usual drag estimations based on velocity. So that falls apart, and therefore we're going to need a completely new approach. This is also why some people just say, rule of thumb, hypersonic flow for a particular vehicle starts around 5 and above, because that's where Mach independence starts. But that's not a very scientific or mathematical way to define hypersonic flow, and we need to seek that. Let's look now at a particular shock layer temperature with particular reentry vehicles, just so you can understand that we have to take into account plasmas. And also we can show through measurement the breakdown of chemically perfect gas. In this particular figure, we have an x-axis of reentry velocity in kilometers per second from 0, 2, 4, 6, 8, 10, 12, and 14 kilometers per second. That's 1,000 meters per second. So our highest speed is about 15,000 meters per second. That's very fast relative to the speed of sound. And so we drop Mach number altogether, and we just talk about velocities of reentry vehicles. On the y-axis, we have the so-called shock layer temperature, which we defined a few slides ago in the particular layer, the boundary layer, to find the maximum temperature. And now we plot the shock layer temperature versus reentry velocity for particular vehicles, an ICBM, an orbit reentry from Mercury and Gemini programs, an Apollo mission, moon mission return at about 11 kilometers per second, and a Mars return mission into the Earth's atmosphere at about 15 kilometers per second. You can see for all these vehicles for 6, 8, 10, 12, 14, 15 kilometers per second, there's two different curves. One curve corresponds to the chemically perfect gas assumption which we made in this class. You can see it departs greatly from, say, 2 kilometers per second and beyond, and 4, and it actually doesn't even, it has such a huge error between, say, the chemically reacting gas models. So using the chemically perfect gas assumption in hypersonics is not applicable at, say, high speeds, or even, say, 4 kilometers per second. And so for high-speed hypersonics, we can no longer use this assumption. Take a few seconds to appreciate the use of a perfect gas law versus a chemically reacting gas. Now, we can also look at associations of ionization and dissociation for air at a particular atmosphere. If we hold our atmosphere at 1 atm, 1 atmosphere of pressure, and we raise temperature, we can look at when particular air dissociates and ionizes. We go from 0 Kelvin to 2500 Kelvin. At 2500 Kelvin, you'll see that O2 begins to dissociate from the flow. At 4000 Kelvin, we start to see nitrogen dissociate, and O2 is almost completely disassociated, where O2 becomes 2O. If we go up to 9000 Kelvin, we can see that indeed N2 almost completely disassociates and ionization of the gases begin, as shown in these particular ionization formulas on the top. And so for hypersonic flows at high speeds, which result in high temperatures, as shown from the previous chart here, we can easily see that our gas ionizes and dissociates, which is, of course, properties of high-temperature plasmas. We have to take this into account when performing our hypersonic calculations. Let's now look at another schematic so you understand the physics of hypersonics and why all our past assumptions are no longer valid, and why this is such a difficult subject. Here we see a schematic of the temperature variation of the specific heat for diatomic gases. That's Cp and Cv, of course. Here we have on the x-axis the temperature in Kelvin all the way to 2000 Kelvin, and we look at the ratio of specific heat, Cp over Cv. At low values, you can see that it rises up and it becomes relatively flat. That is gamma. Cp over Cv is relatively constant near 5/2 between 3 Kelvin and 600 Kelvin, which is a great range for all our flows in this class. And that's, of course, why with temperature we say Cp is relatively constant when we're looking at these, Cp, Cv, and gamma are relatively constant over this range. But once we get above 600 Kelvin, once again, the ratios of Cp over Cv rises again and goes up to an asymptotic value, at least up to 2000 Kelvin, of about 7/2. So this is rather frustrating. And mind you, the y-axis is Cv over R. And so we can no longer use gamma as a constant, or Cv or Cp are constant for high temperatures. We actually have to have models for them within our CFD solvers or calculations. Let's look at another part of the physics of hypersonic flow. Here's the influence of pressure on a particular shock wave temperature in equilibrium air. And we show assumption of the chemically perfect gas and actual measured values as the 3 solid lines for different pressures. One line is 10 to the -4 atmosphere, 10 to the -2 atmosphere, and 10 to the -1 atmosphere. The axis is in kilometers per second from 2, 4, 6, 8, 10, 12, and 14 kilometers per second. And the y-axis is the temperature ratio, the static temperature ratio, across the standing normal shock wave. So for example, in front of the shock, we might have U1 of 10 kilometers per second. Now if we go up, we can see the relative temperature rise for different pressure ratios. You can see the dashed line is a chemically perfect gas assumption, which is what we developed all our equations for in this class. So unfortunately, we'll have to completely develop new oblique shock wave, expansion wave equations for hypersonic flow and normal shocks using a similar theory, but we cannot necessarily make these particular assumptions. This is rather frustrating. Let's now look at particular ideal flows of hypersonics over particular bodies. Let's look at an ideal slender plate. We did this problem earlier in the class for oblique shock waves. If we have a slender plate and we put it at an angle of attack, of course we'll again have an Prandtl-Meyer expansion wave at the leading edge on top with a trailing shock. On the bottom we'll have a very, very, very strong oblique shock wave attached to the pressure side of the vehicle, which of course goes to an expansion wave at the trailing edge once again. So this is very much like the exact same picture we developed for the flat plate ideal supersonic problem for oblique shocks and expansion system in our shock expansion theory class. That's for hypersonic flows, and you'll see that the forces from the shock wave absolutely dominate every other part of the problem. And in fact, the top part of the flow can nearly enter a vacuum above the plate just due to the expansion wave. Let's make some notes on these particular problems and physical observations we made. You see now that linearized velocity potential theory, which we previously used in transonic flow, is not applicable. Pressure coefficients vary nonlinear with thickness ratio and angle of incidence of the particular vehicles. We also see that the continuum assumption is invalid, and we'll have to check the Knudsen number to see if we can use a continuum problem hypothesis, which we talked about in the first classes in this compressible flow field. We also see that the Mach angles must be very, very small so that they do not intersect the waves before and after the shock, and the Mach waves actually closely follow the surface relative to the surface turning angle. All these flows at high speeds for any pressures and temperatures of the atmosphere give rise to hypersonic boundary layers and turbulence, unless, of course, it's a rarefied flow, where the continuum assumption is not valid. We also see that the pressure rise is very large across the shocks especially, so the shock pressure rise dominates the problem. The expansion waves create nearly a vacuum, even in the low angle of attack, high-speed flat plate case. In the next classes, we'll see indeed that this follows closely to the so-called Sir Isaac Newton's corpuscular theory. And so early on, Isaac Newton created a theory of aerodynamics, where he treated it as Newtonian theory of a system of particles. This is a wonderful theory and seems very logical, but unfortunately it doesn't follow traditional aerodynamic theory or explain results. For years, people thought his theory was probably useless until hypervelocity and hypersonic flows came about. We'll look at his theory in the following classes. Today, I just wanted to give you a physical intuition and make observations of hypersonic flow and show you why everything we've done in this class, with the, of course, assumption of ideal gas, is frankly useless for hypersonics. And this is why it's such a difficult field, and for decades people struggled to explain the phenomena of reentry of vehicles into the atmosphere and couldn't make sense of their wind tunnel results of hypersonics compared to vehicles. This is even a great struggle today until, of course, the advent of excellent gas models that take into account plasmas, chemistries into computations. So we looked at these particular observations, and in the next class, we'll start to create a mathematical theory to try and explain the phenomena. Thank you very much for your time today. I'm Professor Steve Miller.